Energy retrofit of a building means a renovation intervention mainly focused on the envelope and technical systems, aimed at improving the overall energy performance. Generally, action is taken on four main fronts: reduction of energy demand, increasing plant efficiency, supply from renewable sources, optimization of energy consumption's control and management. Energy retrofit is an essential tool for decarbonization and sustainability strategies, especially considering the energy and environmental burden of the existing building stock. Through the use of current technologies and installations and the application of standard building practices, it is possible to reduce the energy consumption of existing buildings by up to 90%. More in detail, consumption items that can be most effectively addressed are air conditioning, artificial lighting, domestic hot water. Technological interventions cannot solve aspects of user behavior and the use of equipment and devices, which can heavily influence energy consumption or savings. However, an efficient, interactive and well-organized building system can certainly stimulate virtuous patterns. A deep energy retrofit can be defined as an energy conservation measure in an existing building, also leading to an overall improvement in the building's performance. More in detail, it can be seen as a process of diagnostics, analysis and identification of the most appropriate solutions and their subsequent implementation that aims at achieving on-site energy use reduction by 50% or more. The first example we will analyze is a commercial building on which the retrofit intervention concerned only the envelope. Originally, it was a building designed without any attention to energy efficiency, characterized by poor thermal insulation, large bronzed glass surfaces, no sun protection, dark interior spaces due to the reflective glass, with high consumption for lighting and related internal loads. The intervention was divided into a few main steps. In-depth diagnosis of specific consumption, broken down into the various items such as air conditioning, lighting, hot water and equipment. Identification of possible solutions. Comparative feasibility study based on dynamic energy simulations. Final design and renovation works. The applied procedure was studied and refined in detail so as to facilitate the activities of analysts, technicians and designers and optimize the results. At the end of the operation, this methodology was codified and published as an example of best practice. Going into the details of the renovation work, the opaque facades were reskinned with an insulated and ventilated cladding, with a massive external finish to increase thermal inertia. Reflective glazing was replaced with highly insulating extra-clear glasses, outside of which an automated solar shading and daylighting system was designed, controlled by a predictive adaptive algorithm. An adaptive double-skin facade has been overlapped on the south facade, capable of opening and closing automatically depending on the climate. A BIPV system has been installed on the roof of the double-skin structure with semi-transparent modules configured to produce renewable electricity, but also to cause a stock effect on the interior air, easing its evacuation. As a final result of the retrofit, the building's energy consumption has been halved, saving around 150,000 euros per year. Moreover, thanks to its new functionality and architectural quality of the intervention, the building was revalued by about 4 million euros. Finally, the project was awarded the International Zero Footprint Reskinning Award. The second example concerns a residential building which underwent a deep retrofit as a demonstrator of a recent Horizon 2020 project named HEART. Within the scope of the project, a multi-technology retrofit package was developed, capable of transforming an existing building into a nearly zero-energy building with smart interactive performance. The toolkit makes it possible to intervene rapidly without displacing the inhabitants by improving the performance of the envelope and systems according to a systemic and integrated approach. The following interventions were carried out on the pilot building. Application of a highly insulated ventilated facade. Upgrading of existing windows with new high-performance double glazing. Integration of photovoltaic tiles. Installation of an hydraulic heat pump connected to a high thermal capacity storage tank. Substitution of existing radiators with smart fan coils. Installation of an innovative energy management, dispatching and control system. The core of the system is a cloud-based platform that interacts with the climate context and the electricity grid and interfaces with various stakeholders, such as users and energy managers, in order to optimize the overall energy performance and continuously monitor the operational phases. As already pointed out, one of the most important aspects of the project is that the HERT system can be applied without interfering with the occupation of the inhabitants in planned and sequential phases. The experimental building allowed the refinement of the intervention procedures, which were also evaluated in light of the comments of the various stakeholders. The result of this intervention is a totally renovated building that has reached the NZEB level. Thanks to the reduction of winter losses and summer loads, the integration of a high-efficiency HVAC system, the installation of photovoltaics on the roof, and the use of the cloud-based control and management platform, final consumption was reduced by almost 90%.